A very good afternoon to one and all. Today's session will be taken by Mr. Mendi Balaji, research scholar at NIT Rourkela. He is working under the professor Mona Lisa Patnaik ma'am. He will deliver his speech on the title Design, Implementation and MPPT Control of PMSG based Wind Energy Conversion System. Mr. Mendi Balaji received his MTech degree in the specialization of Industrial Electronics from the National Institute of Technology Rourkela in 2015. Then he joined as an assistant professor at Godavari Institute of Engineering and Technology, Rajamahendravaram in 2016. He is currently working towards a PhD degree from the National Institute of Technology, Rourkela, India. His area of research interest includes the design of DC-DC power electronics converters and the development of intelligent control algorithms for small-scale variable speed wind power generation system. Now I would like to invite Mr. Mendi Balaji sir for his lecture. It is over to you, sir.
Good evening to everyone. I am Balaji. In this session, I am going to explain the design and development of standalone small-scale PMSG based wind energy conversion system using OpenLRT digital controller. So these are the outlines of the presentation. Introduction, dynamic characteristics of PMSG based wind energy conversion system. In that, modeling of turbine, modeling of PMSG equations, and diode model configuration will come. And in the third section, boost converter design and its input output characteristics. In the fourth section, I will going to explain about the system design and hardware implementation of the overall system. So over the 2 decades, the green power generation through renewable energy sources for environmental protection, sustainable development are the major challenges. Among the various renewable energy sources like solar, wind power, tidal, in that wind power generation is getting lot of attention due to its advantages such as cost reduction through government incentives, cost competitive, environmentally clean and safe. Standalone small scale WCS are mostly used in remote and rural areas where the grid connection is not available for the consumers. And what is small wind turbine? According to the literature, the rotor swept area should be less than the 200 meters square, and rated power range is classified into 1 to 15 kilowatt for the residential load applications and 15 to 100 kilowatt for the light commercial load applications. So here the PMSG based variable speed wind energy conversion system is mostly used in the remote areas due to its many advantages, such as increased energy capture. Means PMSG system can easily it can generate power to the over wide range of wind speeds and even under low speed and moderate wind speeds also. So this facilitates effective utilization of the wind resources and increased energy capture when compared to the fixed speed turbines, and it reduces the mechanical stress. PMSG is directly coupled to the wind turbine, or the gearbox requirement is less. So due to that, we know that gearbox is prone to wear and losses. So by avoiding the gearbox, we can reduce the mechanical stress. So that gives less maintenance and increased reliability. In the conventional synchronous generator, the rotor field requires the DC supply for the excitation. Whereas in the PMSG, the rotor field winding is replaced with the permanent magnets so that the external supply for the rotor field is not required. So which leads to avoid of the rotor copper losses. And PMSG based wind turbine which can be operated in the wide range of wind speeds, and it is having high efficiency because due to the lack of external supply, rotor copper losses are zero. So in that way we can say we can get maximum high efficiency, and gearbox leads to more mechanical losses. So by avoiding lack of external supply and elimination of gearbox, these two leads to give the high efficiency. And also due to the less reduction of mechanical components and having high power density, PMSG is having less weight and it can be compactly designed. So this feature is especially beneficial where the offshore wind turbines, when you consider in terms of installation cost and the transportation. And we can say that the PMSG it is having reduced noise and vibration. That is also due to the absence of gearbox. So these are the characteristics of the dynamic characteristics of the PMSG based WECS. This is the modeling of the turbine equations. These are already covered by my colleague Pradyumna Kumar Bera. So here I am focusing on the steady state modeling equations of the PMSG. So the induced EMF in the stator winding is proportional to the angular speed of the generator. Means simply by varying the more the rotor speed, we can get more the generator voltage. And so that equation tells by the equation 5, and the terminal voltage of the generator given extracted from the equivalent circuit of the PMSG, and the generated power is tells by equation 7, and the development torque of the PMSG is given by the equation 8. And here the turbine is coupled to the PMSG and which is interfaced with the diode bridge rectifier. This is the PMSG diode model configuration. So here DC diode rectifier output voltage and current are given in equation 10 and 11. Simply these are we are getting by neglecting the commutating angle and inductance of the converter and the generator. So and equation 12 gives the output power of the wind energy conversion system. Here also we are neglecting power loss during diode circuit rectification. So here equation 13, 14 tells the generated power and torque are expressed in terms of the angular speed and DC current. So this can be and it can be concluded that by controlling the diode rectifier output current, load torque and wind turbine, and finally turbine speed can be controlled. So that is about the dynamic characteristics of the wind energy conversion system. Now I am going to explain about the boost converter basics. So already we are aware of that. So this is here boost converter is used for two purposes. One is it will enhance the voltage level. Second one is used for extracting the maximum power from the wind. So it is a simple non-isolated converter. Here the output voltage of the converter is given as input voltage by 1 minus D, and these are the input characteristics of impedance characteristics of the boost converter. Here converter acts as a load that's why we are interested in the input resistance of the converter. So by varying the duty cycle of the converter, the input resistance of the converter will be varied. So that one is classified by represented by figure 4 and 5. So by operating the duty cycle at optimum level, we can extract the maximum power. These are the input and output characteristics of the boost converter in the wind energy conversion system with the variation of the duty cycle. So on the input side, as duty cycle increases, boost converter input current will be increased, voltage will be reduced. And if you observe, the PV characteristics of the input and output of the converter are different. So based on these characteristics, we can develop various MPPT algorithms. So in the laboratory, we have developed 1.5 kilowatt 220 volts boost converter. For that, the minimum and maximum converter input voltages are 70 volt and 160 volt. And the change in peak to peak ripple inductor current is considered 20% of the converter maximum input DC current, and change in ripple voltage across the capacitor is assumed to be 1% of the load voltage. So load voltage is around 220 volt we have designed. Assume ideal boost converter input and output power are equal. So these are the calculations of the input maximum DC current and converter output current, and duty cycle is calculated as 0.68. The inductor peak to peak ripple current we got 4.3 ampere, and capacitor voltage ripple is 2.2 volt, and the inductor value is V in minimum into V naught minus V in minimum by switching frequency into ripple current into output voltage. So we got around 0.74 millihenry, and the filter capacitor is 141 microfarad. So these all are calculated at switching frequency of 15 kHz. So these are the classification of the MPPT methods for the wind energy conversion system. These are broadly classified into 4 categories. One is indirect power control based MPPT algorithms. Second one is direct power control based. Third one is hybrid MPPT, and fourth one is smart MPPT algorithms. In the indirect power control based, TSR, tip speed ratio algorithm, power signal feedback PSF, and optimal torque control are considered under the IPC based MPPT algorithms. All these algorithms require anemometer and speed encoder for extracting the maximum power. In the classification of DPC, P&O, pattern and observe algorithm, incremental conductance, and optimum relation based algorithms are presented. So these are mostly speed sensorless algorithms. In the classification of hybrid, combinational conventional algorithms, conventional plus smart or intelligence algorithms, and conventional plus optimized algorithms means sliding mode algorithm and model predictive PSO algorithms. Those are mixed with the conventional algorithms. So here I am focusing on the hardware implementation of the basic P&O algorithm. So that one I will going to explain. So these are the mechanical power versus generator speed characteristics. Suppose if we don't use any DC to DC converter, so we cannot extract the maximum power, because according to the wind speed, the generator will be settled to some certain speed, so that it will not give the maximum power. So hence we have to introduce some DC to DC converter to control the duty cycle for extracting the maximum power. So from this graph, at maximum power point, the slope is 0. That means dPm by d omega m equal to 0. With that, we can develop one MPPT algorithm, which is the speed encoder based algorithm. So what we have to do, that one we have to transform to converter parameters. So for that, the mechanic, by neglecting the generator and converter losses, PM will be equal to the DC side power. And also, as I mentioned earlier, in PMSG, the terminal voltage of the generator is proportional to the speed. Hence, the speed is replaced with the VDC. So in this way, dPdC by dVdC equal 0 can be, we can get it. So with that, we can develop the algorithm in terms of PDC and VDC. So this is the P&O MPPT algorithm, which is the most popular speed sensorless method. It does not require any wind speed data or mechanical speed sensor. It is robust in nature against wind speed and load change with simple implementation, which simply requires DC voltage, DC current from the input terminals of the boost converter, and generates duty cycle for the extraction of the maximum power. So this is the flow chart of the MPPT algorithm. So before that, you have to initialize the perturbation time and perturbation step size. Then you have to sense the VDC, IDC and initialize duty cycle and the previous values of the VDC and IDC. Then calculate the PDC, change in voltage, change in current and change in power. So before start searching the MPP, you need to check the DC voltage, whether it is above the threshold value or not. If it is not, the duty cycle will be fixed to its initial value, or otherwise it will start searching the MPP. So once that condition is satisfied, then you have to check the change in power condition. If it is yes, then it will search change in VDC condition. If change in power and change in VDC both are positive, then duty cycle will be reduced. If change in power positive and change in voltage is negative, then duty cycle will be increased. So in this way, we can achieve the MPP by giving the desired duty cycle. So in order to extract maximum power through proper duty cycle, you need to select the proper perturbation step size and perturbation step time. So you cannot give any random change in duty cycle. If you give suppose duty cycle change in duty cycle around some 10%, so means the change in voltage, current and powers of the converters will be more, so which may leads to more stress on the converter. So that's why you have to select the proper delta D max, also delta D minimum. In order to avoid the steady state oscillations, you cannot be very less delta D. Means suppose if you give 0.001, that much change may not be detected by the digital controllers like DSpace, DSP or Popularity. So that depends upon the ADC resolution and tracking accuracy in the steady state. So after experimentation, we have observed that the delta D range is 1% to 5%. So within that range, we have operated. That is the healthy operating range. And next about selection of proper sampling time. So here also, to avoid algorithm divergence and oscillation around MPP, the choice of MPPT sampling time that should be more than the system settling time, which ensures the steady state value of current or voltage. Here we have plotted experimental DC link voltage. There the DC link voltage is settled to around 0.8 seconds. So we can consider sampling time more than 0.8, 1 second or 1.2 or 1.5 seconds you can consider. Now in the next section I will explain about the system design and hardware implementation of the overall system. So this is the circuit diagram of the wind energy conversion system. Here DC motor with buck converter will act as a wind turbine emulator, which is coupled to the PMSG, and PMSG is connected to the resistive load through power electronic converters, AC to DC and DC to DC boost converter. And these are the wind turbine MPPT wind turbine emulator controller, and this one is the MPPT controller. These two are developed in the OpenLRG software. So this is the test bench of the wind energy conversion system. Here all the sensor signals are interfaced to the Wanda box, which is made by the OpenLRG technologies through analog and digital cords. This is the DC motor coupled to the PMSG. So these are the specifications of the wind energy conversion system. Coming to the wind turbine, the cut-in wind speed is 4.8 meter per second. Rated wind speed is 9.5. Means we are generating up to 1 kilowatt wind power. Accordingly, we have considered the cut-in and rated wind speeds. And these are the turbine radius 1.25 meter and air density factor 1.225. Pitch angle we have considered 0. We have designed the wind turbine for 1 kilowatt and optimum power coefficient is 0.48 at lambda optimum 8.1. These are the DC motor specifications. In that we have derived the parameters of the DC motor like armature resistance, armature inductance, field resistance, field inductance by suitable experiments, and torque constant we have developed using no load test, and moment of inertia is calculated using retardation test, and using steady state equation we have calculated the coefficient of the friction. Similarly for PMSG side, the nameplate rating they have given 1.5 kilowatt, rated voltage is 110 volt, and rated line current they have given 8.1 amperes, and rest of the parameters we have calculated. These are the MPPT converter specifications. Here the switching frequency we have considered 15 kHz for the IGBT, and the filter inductance we got around 0.74 millihenry. So we have taken 1 millihenry 30 ampere ferrite core inductor, and filter capacitor 1000 microfarad 450 volt DC ultralytic capacitor we have used. So for MPPT algorithm we need voltage and current sensors. For the voltage sensor we have used LV25P voltage sensor. It can measure up to 500 volt nominal RMS voltage, which requires plus or minus 15 volt DC power supply, and the button resistance range we have to select in between 100 to 350 ohm. Suppose for the MPPT converter you want to measure 300 volt, so that should be have to be scaled down to 5 volt, and these are the, and you need to choose one input resistor. We have selected 30 kilo ohm, so that the input current of the sensor should be around within 10 milliampere. So the button resistance we have calculated 200 ohm, which is the within the range of 100 to 350. So the extra components required is input resistor of 30 kilo ohm and button resistance of 200 ohm, and you need to give external DC supply plus or minus 15 volt. And this is about the current sensor, which suppose if you want to measure current for 25 ampere, and also this is also considered in terms of voltage only, so which is scaled down to 5 volt. Okay, so here we have wounded number of turns two only, because the conductor size diameter is more, so it is very difficult to wound more turns in the diameter of the uh, current sensor. So we have considered 2, and accordingly we have calculated the button resistance 100 ohm. So that is also within the range of the button resistance range 50 to 160 ohm. So here the extra components need to move the turns, number of turns 2, and the button resistance value we have considered 100 ohm. Here also external plus or minus 2 volts is required. In this way we can measure the current. So these are the low power signals. These can be interfaced to the any software like OpenLRT or DSpace or DSP software. This is the wind turbine emulator we have developed in the laboratory. So to drive the ICPT, we have used Skyper 32R gate driver, and the OpenLRT generates 5 volt PWM signal, but to drive the ICPT it requires 15 volt. So bootstrap circuit we have used which will convert 5 to 15 volt PWM signal. So this is the IGBT we have used SKM 75GB 12T4, means 75 ampere 1200 volts which we have used. So this is the OpenLRT real-time simulator. OpenLRT Wanda box in that DSP processor is inside that, and which is made by the OpenLRT technologies. Here the sensors and PWM signals are interfaced through analog and digital cards. For digital card, to produce the PWM signal, you need to give external 5 volt power supply. For that RPS we have used, which is set to 5 volt. So earlier my colleagues has used DSpace for the PV system and for the wind system. Here I have used OpenLRT software. So I will explain how to use this software to interface for the rapid control prototyping. Means rapid control prototyping means the plant is outside where generators, turbine, PV which will be outside. Only the controller is inside the PC. So hardware requirements are host PC required, Wanda box already I have shown, which is manufactured by OpenLRT Technologies, and one LAN wire is required, which is the communication link between PC and Wanda box. The software requirements are RTLab software 10.6.5.293. This one we have used. This is the old OpenLRT, so that's why the compatible software we have used 2011 32-bit version. Now the OpenLRT has upgraded its version MATLAB. It can support for the latest one also. So in this video, I will explain how to develop the MATLAB model, and what are the steps required to execute the model. These things I will explain in this video. So once the software is installed, you need to you need to open the RTLab through Meta controller. You can see there Meta controller is there. Open the RTLab. Here Once you open the RT lab, then workspace will be opened. So that one we have kept it in the H drive. There your model, Simlink model will be presented in the workspace, and data storage also will be presented in the workspace. I have to taking login. It was disconnected. I didn't notice. Video on also. So once the software is installed, you need to open the RT lab through meta controller. Then I have um, I have kept the RT lab workspace in H drive. This is the main window of the OpenRT software. OpenRT software. So once the Wanda box is switched on, then you need to create the target. So mostly it will detect automatically. There you have to address the IP. So here the state is showing up, license is activated. That means Wanda box is switched on. Once the target is set, the next step is you need to create the new project. So here I have given name some wind MPPT. So project is created, which is shown on the left side. So go to workspace, which is in H drive. So there wind MPPT folder is created automatically. So in that folder you have to place 3 files, which are, one is MATLAB model, second one is bitstream file, and third one is configuration file, pin configuration file. So those 3 files I have copy pasted in the folder which we have created. Bitstream file String file enables the library of the RTLab through MATLAB, and pin configuration file is used to identify the pins where we are connecting the sensors and extracting the PWM signals. For identification of that, we are configuring the pin configuration file. It is 1 KB bit file. So in the MPPT Simulink model, where the wind turbine emulator controller and MPPT controller are presented. Once these three files placed in the workspace, so in the RTLab we have to add the Simulink model. I'm recalling that model from the same folder. So model is created. So these are the steps to execute our model. First one is edit the model. Second step is we have to develop the properties. Then build the model. Building means it will generate C code which can be understood by the DSP processor of the Wanda box. Then compilation view. Then you have to assign the targets and execution properties. Then you have to load the model. Once you load the model, that means it is ready to deliver the PWM signal or ready to take the sensor signals. Once you execute, then means it will generate the PWM signals. Okay. So this one I will explain one by one. So you have to open the MATLAB through RTLab software only. Then only the RTLab library will be added to the MATLAB Simulink library. So here MATLAB is opened through RTLab. MATLAB main window is opened. Then edit the model. So this is the model we have created in the MATLAB Simulink. So we have to create two subsystems. One is computational subsystem, another one is for displaying the results. So you need to give naming SM underscore some name you can give, and another block is SC underscore some name. Then only Popularity software can understand, can compute the model. So in this way you have to give the naming. In the SM computational, where entire our model is presented, and this one is for SC model is for displaying the results. And here our emulator controller and P&O controller is presented. And in the configuration parameters, solver type should be fixed step, and solver I have used Ranjikuta ODE4, and fixed step size I have given the name TS, I have given 20 microseconds. 10 microsecond to 50 microseconds we can use. In the model properties callbacks, there I have address TS, which is 20 microseconds. So that in each and every block we no need to mention 20 microseconds. Directly we can call TS name. Power GUI block, there also the simulation type discrete, solver type Rustin I have used, and sampling time there also you have to mention. And the simulation time should be infinite, INF. So this is the model we have developed. In that, wind turbine emulator controller is presented, MPPT controller is presented, and also this software facilitates the storage of hardware data. We can store the data through DSO, or it will store the data in .mat file format. And these are the analog sensor integration and PWM generation. So these blocks are available in the library that I will show. This is the block required OP control OP5142. These all are OP5142 blocks, analog. So in the library, RT events, RT lab, RT IO are added in the MATLAB. Go to RT lab IO. So in the RT lab IO, go to OP5142. There analog in, analog out, digital in, digital out blocks are available. From there we have taken OP5142 op control block. So this block controls the programming of one OP5142 card. It initializes and selection of the hardware synchronization mode of the card. It enables the analog and digital signals. This is the first block we have to add to the model. There bitstream address we have to give. In the workspace, there we have copied 3 files: bitstream file, configuration file, and symlink model. That bitstream address we have to copy paste here. So this is the bitstream file. That address you have to copy in the OP5142 block. Remaining things you keep it as it is. Then to interface the sensor signals, you need to use analog in block. That is also analog in block, that is also available in the RTLab library. So this is the OP5142 analog in block, where we can connect maximum 8 sensor signals. Here I am using 6 sensor signals. For boost converter, 4 signals required: input voltage side, input current, output voltage, output current. And for the emulator, current sensor is required. And for speed encoder also we have used analog in channel. This is the PWM out block. This Wanda box can give maximum 8 PWM signals. Using pin configuration file, we can activate this analog in block. This is the pin configuration file where analog in the number is data out 5. That number we have to enter there, so that it will select slot 1 section B subsection 1 section. There we can give maximum 8 analog in signals. Data out 5, data out 6. Total 2 analog in blocks are there. Means total 16 signals we can connect. Once you give data out port number 5, then that slot information will be activated. So maximum number of analogs in channels we have considered 6. Next thing is PWM out block. The inputs required are frequency and duty cycle, which can be selected by entering data in port 16. So the slot, it is slot 2 section B and subsection 4, which is having 8 PWM out signals. Here I have used number of PWM signals 2. One is for wind turbine emulator controller, second one is for the PWM controller, P and O. So initial phase, since the 2 signals, the initial phase should be 2. If we want some complementary signal, then there you have to highlight that one. That time also we can mention. So next thing is wind turbine emulator controller design, where the modeling equations of turbine are presented. Here CP calculation, lambda calculation, mechanical power calculation, armature reference current calculation are given, and also wind turbine duty cycle, wind turbine emulator duty cycle generation through PI controller also developed. So next thing is sensor signals. These are the six signals. 6 signals we have extracted from the plant. First one is speed signal. There we have used proximity sensor. So that one is connected to the first channel of the analog in. And second one is armature current sensor from the wind turbine emulator. And third one is boost converter input voltage sensor. Fourth one is input current. Fifth one is load voltage sensor, and sixth one is load current sensor. These 6 sensors we have connected from the analog in. This is the speed measurement. Here we are getting some speed sensor signal. That one we are given to the RTE frequency meter that separates frequency and duty cycle. From the frequency, it is filtered and which is converted to RPM, frequency to RPM, then RPM to radian per second. In that way we have converted. These are the sensor signals. This is the armature current sensor. This one is subtracted with its offset value. When you give current sensor plus or minus 15 volt without running the experiment, still it will show some offset value. So that one we are avoiding here. Then it is processed through the low pass filter. We have used 20 by S plus 20. Then it is averaged, and which is multiplied with the sensor gain, so that we will get the actual plant value here. And also PDC sensor also processed same. It is differentiated with offset value, then given to the low pass filter, and it is multiplied with its voltage gain 53.62. This is the VDC actual. Similarly IDC and the PDC we are getting the multiplication of VDC and IDC. Similarly on the load side, V load, I load and P load we are getting. These all are the average values. For MPPT algorithm we require the averaged value. So that's why we have used low pass filters. Next thing about the MPPT controller. This is the MPPT controller. Once the real values of VDC, IDC we get, then these are processed through the P&O algorithm. Then it will generate desired duty cycle. And this block is used for to know the maximum power point. There we have given 1.5% duty change for the certain time period. This is 1% duty change we have taken. the conventional P and O in the flow chart, I said that we have to initialize the perturbation time. So that one I will show how to do. On the math function block, in the subsystem parameters, there you have to mention the sampling time. Here I have considered 1.5 seconds. So that one you have to give it here. By default it will take sampling time TS we have given 20 microsecond. That is very less. This is the MPPT code we have used. First of all, we have to call VDC and IDC. Then PDC is calculated, VDC into IDC. Perturbation step size, here I have considered 2%, 0. So perturbation step size we have considered 2%. Then initialize the duty cycle PDC, VDC. Here D previous we have considered initial value 0.35, D previous 30, P previous 30 watt. Then then write change in power PDC minus P previous. Change in voltage is given as VDC minus V previous. Then mention some threshold value of, if PDC is greater than its threshold value, I have considered 50 watt because we have executed the model for the 1000 watts, so 50 watts which is very less. So that's why we have considered 50 watt. Then check the condition of the change in PDC, change in VDC. All these things I have mentioned in the flow chart. Here duty cycle, it should not go 0 or 1. So in order to avoid that, I have given the range. It should be operate between 0.1 and 0.8. If duty is more than the 0.8, then it will be settled to its previous value, or if duty is less than 0.1, then also it will settle to its previous value. Then update the previous values, D previous, P previous, V previous with its actual values. So that we will go to the next iteration. So PWM out block requires frequency and duty cycle. So duty cycles we get from wind turbine emulator controller and MPPT controller. That one I have given in this subsystem. Here frequency and duty cycle are given individually. Both the wind turbine emulator and boost converter, the switching frequency I have mentioned 15 kHz with some constant block, and these are the duty cycle of the emulator and duty cycle of the PN. In this way only the PWM out block can understand. These are the console signals to display our results in the console block. I have given tracking current, wind turbine side signals and converter signals. All these things we can scope in the console block. So master to SM block to SE block, you can call the signals through the opcom block. Then only it will display the results. So that is available in the RT lab. There opcom block is available. The next thing is about storage of hardware data. For storing the hardware data, you need two blocks. For storing the hardware data, you need two blocks. One is operate file and op trigger. So op trigger is used to store the data between the specific intervals. So here are all the signals are given to the operate file. We can store the data between 100 to 140 seconds by triggering its block. Here number of samples I have considered 10 since all are DC signals. So this data will be stored in the workspace, RTLab workspace, where our model is presented. All the calculations are given here, how to give the size of the operate file block. So we have modeled the MATLAB Simulink model for the controller. Then the next step is we have to set the development properties. There, target platform should be Red Hat. Then build the model so that the SM block will be converted to C code. So model has built. The next step is compilation view. Then assign the targets. Their XHP mode should be on. Then set the execution properties. Their real-time simulation mode should be hardware synchronized. Then load the model. Once the loading is done, then you have to execute it. So once you execute the model, then console window will be opened so that it will start generating the PWM signal. So this is the process of the usage of RTLab software. In the next video, I will show the experimentation P&O MPPT experimental demo. There, here I have given wind speed 8.5 meter per second. Same steps I have said. Build the model. Next step is set the development properties. Load the model, then execute it. Then so that in the DSO it is showing PWM signals. Then we'll start the DC motor. Initially, emulator SPST switch should be closed to protect the IGBT of the emulator. First, you give the speed, so 50% of the speed, so that the armature current will be within the limits. Then we can bypass the emulator switch. That is what I am doing there. Set the field excitation current to 400 milliampere. Emulator switch I am bypassing there. Then set the DC motor voltage to its rated value. I am setting to around 220 volts. Then connect the load. In the DSO, we are showing VDC, IDC and its power. This is the armature tracking current. Once you close the load, switch on the load, then the armature tracking current is increased and DC link voltage is settled to 3 steps, and also DC link current also settled to 3 steps. That one is clearly visible on the DSO, VDC and IDC. This is the armature tracking current. Since we are getting duty cycle 3 steps, so same thing is followed on the all the parameters like CP, generator speed, armature current tracking, VDC, IDC, BDC. Everywhere you will get the 3 step. Meanwhile, you can change the wind speed also. The variable tabler call the wind speed from SM block. There initially we have given 8.5 meter per second. Now I am reducing wind speed from 8.5 to 7.5 meter per second. You can observe the changes also in the DSO. See, I have given wind speed 7.5 so that the VDC is reduced, IDC reduced, the power also will be reduced. Due to less wind speed, there will be less power generation. Now I am increasing the wind speed to 9.5 meter per second from 7.5. You can see the sudden change in the VDC, IDC and PDC. Armature tracking current also increase, which is settled at around 6.5 to 7 amperes. These are the other results of the system. You can these are the duty cycle PDC, VDC, IDC in the scope of the block. You can observe that 3-step duty cycle we are getting there. The VDC, IDC also. These are the load side parameters. Again, duty cycle, load power, load voltage, load current. These 4 results are displayed there. These are the mechanical power, lambda and CP. Last one is CP, which is operating around 0.48, which is the maximum value. That means the turbine is extracting maximum power. So once the experimentation is done, first you have to switch off the turn off the motor, disconnect the load, then turn off the motor and switch on the emulator SPST switch. Once the motor is off, then you can reset the RT lamp. So this is the experimental waveform I have shown in the video. This is the VDC, IDC, and this one is the PDC for different wind speeds. So it is working properly for different wind speeds, for increased and decreased wind speeds. So these are the two. Before executing the MPPT, you should know the MPP. That one we are getting by gradual variation of the duty cycle. So here I have shown the experimental results of wind speed of 8.5 meter per second, PDC with respect to duty cycle, PDC with respect to VDC, and IDC with respect to duty cycle, and VDC with respect to duty cycle. See, as the duty cycle increases, the VDC is reducing. Duty cycle increases means the generated speed is reducing. That's why the generated voltage also reduces, so that DC voltage will be reduced. And means we are loading. Duty cycle increasing means the loading is more. So that's why the current is increasing. So the maximum power we are getting around 635 watts here. These all are the sample results. These are the conventional P&O MPPT results during wind speed and load change condition. This is the duty cycle graph, EDC second graph, third one is the VDC and IDC. So in the same graph I have shown wind speed change and load change. In the duty cycle almost we are getting 3-step waveform, that the same pattern is followed in the remaining waveforms also, in the PDC, VDC and IDC. So in this session I have covered the mathematical modeling of the dynamic characteristics of the PMSG and 1.5 kilowatt boost converter design for the extraction of maximum power, and the design calculation of voltage current sensors, and the test bench demo also I have shown, and conventional P&O algorithm has been implemented on that developed test bench. So these are the references. Any doubts related to this one?
Can you please go to the slide number 12? Where you have shown the variation of the current versus duty cycle.
Yes.
So how the load current is actually here, it is a boost converter, no? So that
Repeat again.
with respect to duty cycle, the voltage will be increasing. So how the load current is, so you have shown increasing, no? That figure. fifth figure. That
Fifth
output
figure, yes.
characteristic
Load
is a
current
boost
versus
converter.
duty cycle.
That load current it is increasing, but how it is possible? Simultaneous voltage and current will be increasing. So it is not amplifier. A converter, the regulator.
See, this is the load current versus duty cycle for boost converter configuration. If you change the converter, you may not get the same graph. That is the behavior of the converter with the variation of the duty cycle.
Yeah, for a boost converter, the output and input voltage, how they are related is 1/1 minus D. Isn't it?
I'm not getting.
The output voltage and input voltage, what is the relation? It is 1/1 minus D into input voltage. Output voltage will be in a boost converter.
Yes.
Okay, so when the duty ratio is increasing, the output voltage will be increasing, but
Output
simultaneously how
voltage
current
should
will be
be
increasing.
reduced. Actually,
Why?
here
This is boost converter.
these are the not the not the boost converter. Here boost converter is integrated with the PMSG based wind system. There we are
Okay.
getting these characteristics. This is not operated alonely. This is integrated with the PMSG system. Then only we can get this kind of characteristics. This one is
Okay, can
expert.
you tell me during the same variation, how the output voltage of the converter will be varying with respect to duty ratio? Have you taken that one?
Means
The output voltage.
output load voltage, right? Eighth
Uh-huh.
one.
The load voltage and load current both are having the same similar figure, similar variations, you can say.
See, mm, in the third figure, PDC, VDC characteristics, and in the sixth figure, load power versus load voltage, both are not having similar characteristics.
No. The load current and load voltage with respect to duty cycle, they're having the same variation.
Yes. Load current versus duty cycle, load power, and load voltage characteristics are same. That's why if you observe the figure 6, their load power versus duty cycle also exhibiting same characteristics. Are you getting from? If you can observe from figure 5 and figure 8, both are having similar characteristics. That's why the load power versus duty cycle in figure 6 also exhibiting the same characteristics.
Okay. Thank you. Another
You
question I'm
cannot
having.
tell me.
Okay. I got it. Another question I'm asking that is a permanent magnet synchronous generator. So means there is no control because it is a permanent magnet. So that's why you're using a DC motor. Why DC motor? Why induction motor also can be suffice because that is having a wide range of control of the speed.
I'm not getting actually what you are saying.
You have connected one DC motor na, to run the PMSG in the
Yes,
emulator you have shown na.
yes, that is the emulator.
But why a
See,
DC motor? It can be a
you
induction
can
motor,
use
no?
any motor. See, the turbine output is mechanical power. So any
Okay.
motor, the output is mechanical only. So that is
Okay.
what we are doing here. Simply we are interfacing with some power electronic converter to reproduce the wind turbine characteristics. People are in the literature. Servo motors are used, induction motors, and PMSM, other kind of motors also they are using.
Okay. Okay. I thought that we might have some another advantage of using DC motor. That's why we have used particularly that one.
DC motor there the controller is very simple when you compared with the other motors.
Okay. Okay. Thank you.
Okay, any questions from participant? Any more questions? Okay, then we would like to extend our heartfelt thanks to Balaji sir for his detailed discussion on operative implementation in wind energy conversion system and implementation of MPPT techniques for the control of PMSG based wind energy conversion system. Thank you so much sir. And with this we conclude today's session, and tomorrow we'll start at 9:30 a.m. by Professor Biswajit Ghosh sir. Thank you everyone.